All right, we got a warm up for you today. And to point you in the right direction, because you may not ever get this. This is cosine x cubed. And if you try doing u equals cosine x, du equals sine x or negative sine x dx, we don't have a sine x in here, so this doesn't work. That's a no-go. So what I recommend you do is recognize that this is cosine x times cosine squared x dx. And recall that cosine squared x plus sine squared x equals 1. So cosine squared x equals 1 minus sine squared x. And that changes your problem to this. For 5.4, that horrible, all that K shit, the sigma stuff, I recommend doing a few problems, but I'll tell you right now, I'm not having that on my test. That it just takes up way too much time and energy and paper to fucking do any simple problem in any other method. It's a stepping stone. Now, if you're going to be a pure math major, you better know how to do it, because you go into harder classes like a upper like university, you'll be doing way worse than that. But I don't think anyone in here is a pure math major. What did Matthew? So what should I do my U sub on here? It's not going to work here. We just showed how that won't work. But I'm glad you're coming in swinging. Pay attention. Well, we've got this 1 minus sine squared x in parentheses. I could try 1 minus sine squared x. And I think if I were doing this myself, I would try that. I know it's not going to get me to where I want to go, though. This would be negative 2 sine x times cosine x dx. That didn't help. That's a no-go also. So maybe try u equals sine x, because I don't have another sine x out here. But if I have u equals sine x, du equals cosine x dx. So these two together make my du. And I can write this as 1 minus u squared. So that's what's going to happen. It's going to turn into the integral of 1 minus u squared du. I know when I was a student, I very much wanted dx by itself, and I would divide through by cosine x. So if that's what you want to do, you're more than welcome to do that. You can say du over cosine x, and then plug that in, and you'll see that I'm just going to do it over here. The cosine x cancels, and I get to that. With a little practice, I found just leaving this as long as it shows up there, it makes it an easy substitution. You just got to identify what pieces make it up. And they do have to be multiplied together. Everything needs to be multiplied here. And that works. So if I integrate this, I get u minus 1/3 u cubed plus c. And we put sine x back in. And I've got sine x minus 1/3 sine cubed x plus c. Yes, that was more from 5.3. The u subs is probably one of the harder topics for most students in this chapter. 5.4 is a pain in the ass, but I'm not going to test you on it because it's really just look, this is how we got to where we're going. The end result is much easier. This is going to get all it's going to clean up nice and pretty.
So we're not doing sigma notation on the test?
Correct.
Oh, nice.
Well, on the final, there might be limits and shit. Limit doesn't have sigma, though, does it? No, yeah. I don't think I'm doing sigma. Just should still know how to do it, do some problems with it so you understand everything. All right, so let's hit what we're going to start with today, 5.5. Did anyone need that up longer before I start yanking shit? And ask. All right. So 5.5 is on Riemann sums. So what we've been doing is we've been breaking this up into delta x, where delta x is the same width. Delta x was the same for each subinterval. That's what we were doing. Riemann sums, it's two n's right there. There we go. Riemann. It looked like an M at the end. This was how we did it the old way. Riemann said, what if they aren't equal widths? They aren't equally what? What if we had some shit like this? We're like, oh, this one's fairly flat here. We can make it pretty wide. But where it gets a little bit steeper, we're going to do it a little bit narrower. And where it flattens out, maybe we'll widen it back up. And then when it gets steeper, we'll go shorter. So different widths. Still trying to find the area. Remember, that's the end goal here. Find the area is the end goal. So what he says, all right, they're equal widths. Let's just find the one that's the biggest width. Let's call the biggest width. I don't know. This one looks like this might be the widest, but not by my, I can make it the widest by just adding another fucking line over here. There we go. Now it's definitely the widest. We'll call this our max delta x. And now rather than limit as n goes to infinity, what we're going to do is we're going to do limit as max delta x goes to 0. So whatever's the widest rectangle, we'll make that one go to 0. All the other ones go to 0 a little bit faster. And we still get the same idea as n going to infinity because we have end up with rectangles of 0 width. That was the concept of n going to infinity. The rectangles went to 0 width and we had the actual area. So that's what we're going to have. Our area now shifts to the limit as max delta x goes to 0 of the summation of k equals 1 to n f of x sub k times delta x sub k. And if it's over a region from A to B, and if f of x is continuous, we're going to write this in two parts here. There's two theorems that go with this. They're completely related, but there's a big difference. If f of x is greater than 0 for all x in AB, then this is the area. Equals the area. And it also equals the integral from A to B, written like that, of f of x dx. And this is the area. I said greater than 0, but it could be greater than or equal to 0. The other half of it in general is there's no restriction on f of x in terms of value. So this would be the net area. But it's still the same thing. Integral from A to B of f of x dx. It's now called the net area. So one requires f of x to be positive everywhere, and then you don't have any negative values. That's part A. And this would be like part B. There's negative regions. I said no restrictions in terms of value for part B, nor in continuity. As our first example is going to show you, f of x for part B, f of x needs to be integrable. That's a weird word to say. Integrable. Or able to be integrated. It's the thing. Doesn't need to be continuous. You guys ready for the magic? It's not really magic here. Not yet. Like for me, I was an applied math major. I would personally gloss over 5.4 and 5.5 as fast as I can, but it's required that you see it and have seen it because 5.6 is based on something called the fundamental theorem of calculus, and it's based on this. And I can't really say what it is without showing you this. And since it's fundamental, it's like the heart and soul of calculus, part of the heart and soul of calculus. Like the derivatives got the shaft. It didn't get a fundamental. You guys ready? Let's do integrate -2 to 3 of f of x dx, where f of x equals 2 for x greater than or equal to 0 and 1 for x less than 0. All right. For x greater than 0, the value of f of x is 2, which is a flat line. And that goes up to 3 and stops. For x less than 0, it's only 1. Definitely not continuous, right? The function jumps in value at 0. Continuous? No. Integrable? Yes. We can find the area, right? In fact, if I call this A1 and this A2, A1 has a height of 1 and a width of 2. So height times width, or maybe I'll call this length. Length of 1, width of 2. So L times W is 1 times 2 is 2. A2 has a length of 2 and a width of 3. So L times W is 2 times 3 is 6. And the total area is A1 plus A2. 2 plus 6 equals 8. Now note, I can write this as area here was negative 2 to 3 of f of x dx. I wrote this area as area equals a1 plus a2. A1 was negative 2 to 0 f of x dx. And a2 was 0 to 3 f of x dx. So that's very much a valid operation. You can break up an integral into parts to do it over different regions. As long as the regions are all, you get all the regions. So some generic, because we're just doing area right here. We haven't examined what putting these symbols on here mean in terms of how we're going to use it in integration. We're just showing these are the boundaries of our integration. So that's what these are called. The negative 2 and 3 are called the limits of integration. And in general, that's the A to B. They set the boundaries for the area we're looking for. So let's give you a couple rules. Yeah, press.
So will this one work if it's not continuous?
What?
If like the roots are there, will it work if it's like not continuous?
This isn't continuous.
Oh, I mean, no, if it is, sorry.
Oh yeah, yeah. If it's continuous, it's the same thing. Yeah, it's a good question. In fact, generally, if it's not continuous, you want to break it up like this because your f of x is going to have different things on each one. And like if we didn't have these numbers on here, integrating this, doing the antiderivative. See where this is leading in like a half hour, we're leading to doing antiderivatives. Something's going to be involved with these numbers, but f of x is different on those two regions. So what you integrate it to is going to be different on those two regions. So you really want to break it up if it's not continuous. That's a really good question. I'm going to write that down. If f of x is not continuous, like that last problem, you must break it up into different integrals. You solve it. Okay, a couple rules to live by. Rule 1. The first rule of Fight Club is there is no Fight Club. Yeah. If we integrate from a to a of f of x dx, this equals 0. A to a means we have no width. There's no width. A rectangle of no width, length times 0, or length times width, is 0. Makes sense. Seemed funny when you first hear it, but once you think, oh, area of a rectangle, kind of makes sense. This next one is really trippy. I kind of like it a lot. If we have a to b of f of x dx, this is the same thing as doing negative b to a f of x dx. You can change the order of integration by introducing a negative. Rule number 3. A lot of these rules stem from limit rules. This Riemann, this is based off a Riemann sum. The Riemann sum had a limit in it. And so if we had a constant inside of a limit, what could we do with the constant?
Pull it out.
We could pull it out. Same premise here. Just like limits. We also had, if we had two different things added together inside of a limit, we could break it up into two limits. We actually just should have said one of them, but I didn't make it an official rule. If C is in AB, kind of like we have A, C, B like that, then the integral of A to B f of x dx can be broken up into two integrals, A to C plus C to B. Yes.
This is kind of unrelated, but I've been thinking about it. Why in basically everything, for example, the mean value band, it's always from A to B, in between them the value C, not A to C.
Because they don't always need the C in there. So they like to keep it alphabetical, A to B. I'm with you. Here, I'm literally fucked up the alphabet right here. But they teach A to B in the beginning where it's simple, and then to not change shit up and make it confusing, like all of a sudden, we were gonna do an A to B, what the fuck is A to C? We just say it would maybe I'm using C is the wrong thing. Let's just say there is a smiley face. So we're going to do A to smiley face and smiley face to B. That doesn't fuck up our language now, does it? Our system of our alphabetical system. But learn to speak, David. That's the great thing about using variables. We can use whatever the fuck we want, as long as we say what the variable is. If you use smiley faces and frowny faces and shit like that as variables on your test, as long as you let me know what the variable is, like you don't need to do a U substitution. You can do a fucking smiley face substitution. Make your day brighter. Do a smiley face substitution. Just tell me what smiley face is and what the derivative of a smiley face is if you use it as a U substitution. I'll get a chuckle out of it. I've done it myself. I've had teachers laugh at me to my face for it, but give me full credit because it was correct. I said I got tired of using the same fucking letter. And if I didn't like the problem, it got ugly, smiley face quickly turned to a frowning face because it was no longer fun. Wait, people are still writing. I need to not move this yet. All right. Like rule 6, I could say rule 6 and 7. I mean, I think they described all these as theorems, but if f of x is greater than 0 for all x, remember that's for all in a to b, then the integral from a to b of f of x dx is greater than or equal to 0 also. The function is positive everywhere, the area is going to be positive. Yay! This makes sense. Rule 7 kind of builds off that, but generalizes it. If f of x is greater than or equal to g of x for all x in a to b, then the integral of f of x from a to b dx is greater than equal to the integral of a to b g of x dx. So like rule 6 is really the same thing as rule 7, but G6 is 0 in rule 6. It's the same idea. That's it for all the boring rules in this. We're just going to apply some, and then we're going to like switch to the good shit. This thing right here, a to b f of x dx, I guess they didn't really give it a name. This is going to be called a definite integral. As opposed to indefinite, which we had earlier.
Does that mean when we integrate that, is there still going to be a constant of c or no?
You'll see. Wait for it. It's the magic. It's part of the unveil. You don't want to see what's behind the curtain too early, do you? You gotta be introduced to all the sexy parts one at a time. The curves, the gorgeous curves of these things. All right. Let's do an example. Let's do 2 examples. Anyone needs this up still? You're sitting there like, boys, I don't know if you're waiting to write down one last idea or what you're doing. All right, let's do 0 to 4 absolute value of x minus 3 dx. So like let's show the integration setup, and then let's find it using geometry. And 2, find with geometry. So absolute value of x minus 3 equals x minus 3 if x is greater than or equal to 3, or negative x minus 3 if x is less than 3. This is like x minus 3. That's our function right there. Brightness went up. So it like switches at 3. Which means we're going to do 0 to 3. This has 2 different parts. It's got different values. So this line is the negative x minus 3 for 0 to 3. And then from 3 to 4, it's actually x minus 3. Like if you rewrote this, this would be, this line right here is y equals negative x plus 3, which is negative x minus 3. And this line is y equals x minus 3. It's 2 different lines basically intersecting. That's how absolute values look. That's what it would be integration. We haven't learned how to do that yet. Yeah.
So like 0 to 4, there are A, B, and then 3 would be our C.
3 is like our C, yeah. Okay. Or smiley face, since Dalton doesn't like using C. So, fuck your C. It's not in the right order. Use A prime. A.2. All right. Geometrically, what do we got going on here? This is a triangle. So we call this like A1 and A2. So triangle, what's the area of a triangle? 1/2 base times height. So for A1, what's the base and what's the height? Base is 3. That's correct. How do I find the height? What's this value over here? It's the y-intercept, which is x equals 0. Plug in 0. Because this is y equals x minus 3. If I want the height, y, it's just 3. Absolute value of negative 3 is 3. And I write it like that just to make sure everyone sees where I got it. So A1 is 1/2, 3 times 3. is 9/2. A2. What do we got for base and height? One and one. If I plug in 4, 4 minus 3 says this height here is 1. So 1 and 1, and so A2 is 1/2 times 1 times 1 is 1/2. And our total area is A1 plus A2. 9/2 plus 1/2 equals 10/2, which equals 5. You don't have to overthink like what the height is. Just plug in your x value and find out what f of x equals. Okay? I know a lot of people look at it and go, what is that? I don't know. Like they gave us a formula specifically to find it. Let me give you guys one to work on for 5 minutes. Do it together. And you stretch it and you got a question, man. Stretch it. A couple people are still writing. I don't want to yank this yet. Anyone do anything fun for Thanksgiving?
Dinner,
Dinner's like always fun.
like other than just Thanksgiving.
Like going there, like are you staying home or going to someone's family's house, like a family member's house, anything fun?
And
And is your uncle fucking insane?
mine,
Yeah. Like it always seems like no matter where I go, everybody has like an Uncle Bob that's just fucking batshit crazy, like acts funny.
this is your second husband.
Oh,
Same as my uncle.
so maybe the original uncle was batshit
He
crazy.
was, holy shit. I didn't realize that. He was great. It was fun though.
They usually go together. They quite frequently go together. I doubt his name was Bob. That would be funny. I just use Bob as a general name. All right. Your guys' job. -1 to 1 square root of 1 minus x squared dx. Just geometrically. And in case you don't know what the geometry, does anyone know what the geometry of that is? This stems from x squared plus y squared equals 1. So y squared equals 1 minus x squared. Y equals square root of 1 minus x squared, but it's the positive half, so it's only above the curve, or above 0, above the x-axis. This problem, it actually could be, once you've seen that part and realize what you're doing, this could take you less than 10 seconds. As long as you know the area of a circle. I got Matthew. You can see it. He does it.
Pi squared.
Ah, damn it. I don't got him. Yeah, it is pi squared. And if you didn't know how to graph that, that is what you should do. You should start here and like work backwards. Go, okay, let's square it. Let's get rid of the square root. And if I put them together, does that look familiar? Yeah. That's a circle. What's the radius here? 1, because the right side is r squared. Area is pi r squared for a circle. Circle. So what's the area here? Pi r squared over 2, but r is what? It's 1. We're going from -1 to 1. We just got done saying r was 1.
Right.
So area of the full circle is pi times 1 squared. It's pi, but we only have half a circle. 1/2 pi r squared is 1/2 pi or pi over 2. So earlier I said we can do this integrable thing as long as it's integrable. But like I didn't give I showed an example of one that is integrable, but I didn't give really like how the hell do I know if it's integrable or not? So maybe we should like finish off with that. A function is integrable if there is an m greater than 0 and we're also going to require f of x is bounded on AB. Let's try this again. F of x is integrable if f of x is bounded on AB and there is an m greater than 0 such that negative m is less than or equal to f of x, which is less than or equal to m for all x in AB. So not only is it bounded on left and right by AB, but there's a min and a max. Like min and max. They specifically chose the same one. We could choose the one that's further away because they're going to use it in a little bit in 5.6 to show the mean value theorem for integrals. Yeah.
Wait, so with the graph like an asymptote, would that not be integrable?
F of x equals 1 over x is not integrable. As long as 0 is in the domain or is in the region. That's an excellent identification of that, Preston. If we have f of x equals 1 over x on AB, if 0 is in AB, f of x is non-integrable. Because we have that. And as x goes to 0, is either positive infinity or negative infinity, depending on which side you go from. Which means it has no boundary. From 1 to 3, yes, we can do it. So it's whether or not it's in the domain. So there's a couple things that will speed this up, this identification. If f of x we're going to let f be defined on AB. What? If f is continuous, it is integrable. I'm tired of saying that word. It sounds awkward coming out of my mouth. Does it sound weird? Integrable? If f is bounded, and has a finite number of discontinuities, it is integrable. The hell? That ain't right. And I guess you could go, if it's not bounded, it's not integrable. So it's kind of helpful to identify what isn't. Let's take a 5-minute break and we will start 5.6. 5.6 is on the fundamental theorem of calculus. So we're going to look for the marginal profit for a product. Well, we have the marginal profit for a product. P prime of x is 150 minus x over 10. Where, I didn't write this, where x is the number of units produced. Find the change of profit from 10 to 20 units. So P of x is the profit function. So we need to integrate P prime of x dx. And if we do, we get P of x equals 150x minus x squared over 20 plus a constant. So the change in profit would be the profit at 20 minus the profit at 10. That would show us how much it's gone up. So we have 150 times 20 minus 20 squared over 20 plus C minus 150 times 10 minus 10 squared over 20 plus C. That's 3,000, that's 20, that's plus C. And I've got minus 150. 10 squared is 100, 100 divided by 20 is 5. The minus distributes to each of these though. So minus and a minus turns into a plus. That'll be plus 5 minus C. So 3,000 minus 20 is 2980 minus 150, 2880, 2830 plus 5 would be 2835. Wait, that's 1,500. That's wrong. That's not 150, that's 1,500. 3,000 minus 1,500 is 1,500. Minus 20 is 1,430. Plus 5 is 4. And I'm sorry, 1,480 plus 5 is 1,485. There you go. That's a little bit better. 1,500 minus 15. Yeah, 48, 1,485. Notice, and this answers your question, Matthew. Notice the C's cancel. Definite integrals don't have a C. In the answer. Because we took the integral there, but really, if we compare this to what we did in 5.5, our boundary was 10 and 20, so I would put that there like that. That's what we put for our boundaries. So this was a definite integral. But I showed it without doing the definite integral with the C and what happens if you deal with it. And notice, like reasoning it out, this is what had to happen in the end. P20 minus P10. We integrate and we do the upper boundary minus the lower boundary. This is actually the fundamental theorem of calculus. So I will write that out when everyone's ready for it. You guys ready for more? Fundamental theorem of calculus. Well, the first one. First fundamental theorem of calculus. If f is continuous on AB, And big F is an antiderivative of little f. Also on AB. Then A to B of f of x dx equals f of b minus f of a. That's crazy. The area under the curve only amounts to what are the values at the endpoints. It's fucking mind-blowing. Well, these are different functions, mind you. So area under the curve of the derivative relies solely on the values at the endpoints. Of the original function at the endpoints. Because remember, f prime of x is little f of x. That's what antiderivative means. So if our original function, this is, by original function, I mean big F, and the derivative is little f. Yeah.
So I'm confused. So the two capital S's, they're different functions?
They're the same function.
They're the same function.
Evaluated at different points.
Values you plug in A and B.
Yeah.
Okay.
They're the boundaries that they're the same A and B we've been doing for the area pictures the whole time.
So wait, would this work if your area goes into a negative
It
value?
does.
Okay.
It's showing the net area though. Because if we have negative regions, it's only showing the net area. So we can actually prove this. You can prove this using the mean value theorem. For each sub part because remember, this is the integral means partition into n sub different partition into n sub intervals. So we have n of these. We've got x0, x1, x2, x3, x4, x5. The x values there. So let's say we're looking at the x sub k interval or x sub k minus 1 interval to x sub k. Whatever k is here. The mean value theorem says, as a reminder, there is some point in the middle where f prime at that value equals the two different ones Let's see, this is x sub k minus x sub k minus 1. That's the mean value theorem. We use little f. We just said f of x and shit like that. But let's show what this looks like if we write out the curve. So my line underneath, it starts at A, then I have x1, then I have x2, then I have x3, and then I have B. This is n minus 1, x sub n minus 1, x sub n minus 2. So if I solve this real quick for f of x sub k minus f of x, I just lost my lamp. That is really bright. If I multiply through by x sub k minus x sub k minus 1, I have f of x sub k minus f of x sub k minus 1 equals f prime of x sub k star times x sub k minus x sub k minus 1. God, those x's and k's are fucking confusing me as I write them. They look they're too fucking similar in writing. Well, our first one, I'm doing k equals 1. I have f of x sub 1 minus f of a equals f prime of x sub k star in there times x sub 1 minus a. This is the thing we were doing in the Riemann sums. I'm not on k, this is x sub 1 star. F of x sub 1 star times delta x1. And when I do k equals 2, I have f of x2 minus f of x1 equals f prime of x2 star, x2 minus x1, which is f of x2 star delta x2. Thank you.
Merci.
Thank you. If I do k equals 3, f of x3 minus f of x2 and this is f of x3 star delta x3. But all these delta x's are the same. If we get down to k equals n, well, when k equals n, I'm at b. I have f of b minus f of x sub n minus 1 equals f prime of x b star b minus x sub n minus 1. That is f of x b star
Well, and that's the nth one. Should leave that the correct notation. Delta xn. So there's a little gap in here where I didn't write down everything. But the integral from a to b, f of x dx, is the summation of these. Summation of f of x k star delta x k. So we are adding these up. Add this shit up. Those cancel. Those cancel. When you get down to the bottom, these will cancel. The only things that don't cancel because we're adding up these, we're adding those, which means we're adding these, but that's negative f of x1 and that's positive f of x1. Those go away. Negative f of x2, f of x2, those go away. All that's left over, that bad boy, fb minus fa. It's all that's left over after you cancel up all the subintervals. Crazy, right? Do we care about that though? Well, if you're a pure math major, it's kind of good to know that there's support for me just saying plug in the numbers, because like plugging in the numbers just seems like a magic pill. You know what I mean? But like there is some mathematical evidence. How are we going to use this though? We're just going to plug in the numbers. Ready? Let's put this to use. Enough of the boring shit. We've been doing boring shit for like 3 hours now. Like Tuesday's lecture wasn't any more fucking fun. Negative 2 to 3 of 1 plus 2x dx. The way we show dealing with those limits of integration is we integrate like normal. So what is the integral of 1 plus 2x? What's the integral of 1? X. What's the integral of 2x?
2x cubed.
Yeah. So we go up a power, divide by a power. So it goes up to 2 on the power, divide by the 2, x squared. The way you show the limits of integration is you make this big vertical, you put the shit in parentheses, and you do this. That's how you show how you're going to evaluate it. This is common notation. If it helps, you might like putting x equals negative 2 to x equals 3. That's another way of writing that, but the shorthand is just negative 2 and 3. Putting the x actually comes in pretty handy when you start doing multiple variables. But that's in calculus 3. Not so important right now. So what this means is I am going to do, I've got x plus x squared going from -2 to 3. That is 3 plus 3 squared minus -2 plus -2 squared. So f of b minus f of a. Because this is our big F. That's my big F of x. So I've got 3 plus 3 squared is 3 plus 9 minus -2 plus 4. 12 minus 2 is 10. We quickly found the area under the curve with all that fucking sigma notation bullshit that took forever to fucking do one problem. You know what I'm talking about. I made you feel the pain for a little bit. It's better to feel the pain on the homework and see how it works than have to do the pain on the test. All right. This kind of actually shows what happens if we do A to A. A to A of f of x dx is we do big F of x evaluated from A to A, f of a minus f of a equals 0. I told you that integral equals 0 earlier. Now we see another way how it confirms that. Ready for a little bit more? Nope. I see some pins still going. This actually is how you can show the other rule that we like. A to B, f of x dx equals negative b to a, f of x dx. This is going to be f of b minus f of a. This is going to be negative f of a minus f of b. What if we had like the integral from -1 to 1 of 1 over x squared dx? We actually can't do this yet. It may look like we can. Because you may want to do this. You may want to say -1 to 1, this is x to the -2 dx. So if I integrate this, this is up a power would be x to the -1 divided by the power. So I have -1 over x evaluated from 1 to -1. That's what you want to say based on our rules. But that is f of x equals 1 over x squared. It is not continuous on -1 to 1. So wait for Calc 2. They will address how to deal with these things. We can see there's a asymptote. You'll see in Calc 2 how to deal with those.
So wait, so it would work?
You'll see tools for making it work.
I just thought I just couldn't do it, like it just wouldn't work.
Some cases it doesn't work, some cases you can get it to work. So wait for it. Just know that the harder shit will be gotten to eventually. Guys ready for a little bit more? So this is where we get the mean value theorem for integrals, where this is going to show like the thought process here. Let's say we've got a equals the integral from a to b f of x dx. That's our f of x. Here's a and here's b. So that's f of b. And that's f of a. We'll call this big M, like the max value on that region. So M will be max. And we'll do like little m. For this one, little m will be min. And in my picture, they just happen to be the endpoints, but they don't have to be the endpoints. M and M do not have to be the endpoints. They should be the max and the min now. Or min and max, the way I wrote the letters. We know this exists by the extreme, we know these two exist by the extreme value theorem. M and M exist by the extreme value theorem. Finding those extrema and shit like that. We did that a few chapters ago. So like, maybe I'll call this little rectangle here. That's R1. And we'll make the big rectangle, if I go up to the top, R2. Can we all see pictorially that the area of R1 is less than the integral of a to b f of x dx, which is less than the area of R2? I think that's easy to see graphically. But this is just M times B minus A. And this is big M times B minus A. That's the area of a rectangle, length times width. Okay, so if we divide by B minus A, I get M is less than 1 over B minus A to B f of x dx is less than M, big M. Or maybe I'll write min and max to make it a little bit clearer right here. The mean value theorem is there somewhere in here that's the middle. Let's say it's right there. Let's say that's C. I don't know if that's C or not. Doesn't look like it. There's some rectangle in the middle. That's the average of those two. There's some rectangle in the middle, and we had this as f of A and f of B. This is going to be f of C times B minus A. That'll be the height, that'll be the width. So if I go back up to AR1 and AR2, I had AR1 is less than f of C times B minus A, which is less than AR2. And that's where we put min in again. Min B minus A is less than f of C. B minus A. And max B minus A. And we get the min is less than f of C, which is less than the max. These two compare. there exists a C in AB such that f of C, such that the integral of a to b f of x dx equals f of C times b minus a. Is that how they have it set up in the book? There's two ways of looking at this one. I'm going to go the way the book shows. Yes, this is how they do it in the book. So, like, to do like an official proof, that looked a little jargony. We're going to do the integral from a to b of m dx. So the min, we know that's less than or equal to the integral of a to b f of x dx. And that's less than or equal to the integral of a to b of the max dx. Like if we're doing those rectangle things. This is the rectangle concept again. If I integrate this though, this is min times x evaluated from a to b. We're not evaluating the middle one. And this will be max times x from a to b. This is where we get min times b minus a. If we plug in the evaluation, they divide. And then they apply the intermediate value theorem. The IBT says there's a C in the middle. And to get back up to this, multiply both sides by b minus a. Which is just a number. So to show you the second fundamental theorem in calculus, I need to like point out something real quick. If I go a to b of f of x dx, that's the same thing as doing a to b of f of t dt. It's the same thing as a to b of f of u du. If x equals t equals u, they're all just variables here. So if we want to integrate to x, we don't want to use f of x dx. Does that make sense? So let's use t. The second fundamental theorem of calculus is this chapter still the same chapter? Am I working ahead? Nope, it's here. Let f be a continuous function on an interval I. And let A be a point in I. If f of x is defined as I don't want to use x. I just said don't use x. F of t, t, t. Then f prime of x equals f of x for all x in I. That is a very, very, very confusing way to illustrate this. Because this means d dx of f of x. So we're going to do d dx of that, which is d dx of that. Here, note x is the upper limit. And we do require it to be continuous. I'll make a video this weekend to show the proof, but I want to walk through a problem real quick. It's pretty quick. So let's say we've got find d dx of the integral of 1 to x t squared dt. So we could do this, we could do ddx. If I integrate that, that is 1/3 t cubed evaluated from 1 to x, which is ddx of 1/3 x cubed minus 1/3. And I take the derivative here and I just end up with x squared. That's working it out the slow way, taking advantage of the fundamental theorem of calculus, part 2. So f of t equals t squared. So this is going to turn into f of x, which is x squared. If I gave you ddx of the integral of 4 to x, natural log of x, or natural log of t dt, what should we get? Let's make it even better. Let's do like t cubed. You really want to go through and try to do all this work up here? No. Jump to evaluating it at the upper limit. So A is a shitty method on this one. B is easy as pie. You just have to remember it. With that, it's 10 o'clock. I hope you guys all have a wonderful Thanksgiving.